Good morning. So, in continuation with our previous discussion on two-dimensional materials other than graphene, so if you remember, we have discussed about silicon-based two-dimensional materials, silicene, and germanium-based two-dimensional material, germanium. Today, I'm going to discuss two more materials known as phosphorene and stanene. So if we talk about phosphorene, so this material have also attracted a lot of attention in 2014 and 15, and even in technical news also, such as you can see here, the phosphorene excites material scientists, physicists look past graphene for atom thick layer that could be switches in circuit. So basically, it has some kind of additional advantages over graphene or that electronics properties which are not seen in case of graphene, that is very much relevant for digital electronics or the switching circuits. So therefore, even the news was graphene rivals phosphorene is bound to be a transistor. Even the superconductivity of phosphorene was also investigated and reported. And even this number of publication versus year plot demonstrate the popularity of this particular material. Even if you see the jump in the number of publication in 2014 to 16, within this 12 year, the graphene, TMDC, and boron nitrate is having the increase, it's not very random, it's basically increase in a slow pace. However, the other materials such as phosphorine, amexine, they have shown very high tendency of the increase in the number of publication, and within even 2 years, 14 to 16, if you see the phosphorine is rise from 10 to the power 2 to or 10 to the power 3. Even this figure shows the number of publication for black phosphorus here. So see, suddenly there is a jump in 2014, 15, 16 because it includes the publication of phosphorine, which is shown here in index here, the number of publication on phosphorine. So in within 2016, even more than 250 publications are there. So all this shows the phosphorine become a very popular material due to several different properties as compared to the graphene, and very relevant material for electronics application. So if we talk about fabrication or synthesis of phosphorine, so here again the bulk black phosphorus has the layered structure, or we can say it is a van der Waals material, similar as in case of graphite. So now here also the layer of phosphorus can be detached, exfoliated, and then we can achieve the phosphorine. So top-down technique similar to the graphite can be used to fabricate the phosphorine from black phosphorus. And how we can synthesize black phosphorus? So we can use a different techniques such as high pressure, high speed ball milling, short transport reaction, and polycrystalline black phosphorus can also be developed by using red phosphorus under high pressure. And then that red phosphorus can be converted to black phosphorus, and then it can be used for fabrication of phosphorine. So both basically red phosphorus as well as black phosphorus can be used as a precursor material for synthesis of phosphorine. So what is the difference when we are doing the exfoliation? Basically the interlayer cohesive energy in case of black phosphorus is very high. It is almost 151 millielectron volt as compared to the graphite, which is very, very less. So here we need to supply a very high energy if we are trying to separate out the layers. However, it is possible, and mechanically as well as liquid exfoliations of black phosphorus have been reported, and the result have been demonstrated the achievement of monolayer or bilayer or few layer phosphorene. Other techniques such as pulse laser deposition or by using plasma, this kind of exfoliation has been demonstrated and phosphorene was fabricated. The structure of phosphorene is slightly different as compared to the graphene. It has something different, a kind of puckered structure in, and where though it is having a single layer, but all atoms are not in the same plane. I think it can be understood by looking this figure. So if we talk about phosphorus, phosphorus is basically having an orthorhombic structure, and in which the phosphorus atoms are bonded to each other or neighbors using covalent bond. So three other neighbors are attached with a covalent bond, and therefore the structure is also have sp3 hybridization. It's not like in case of carbon sp2 and then the z direction is just pi interaction. Here it's kind of sp3. So basically the atoms are localized, like two atoms are here, then one atom is down. So this kind of structure is there. Then the other atom is down. So let's say this kind of zigzag structures are there. So here, therefore, we are having one set of atoms at the down plane and another set of atoms at the top plane. You can see the side view here. If you see my cursor, the black atom and the gray atom. So basically, they show the two different height. So each single layer of honeycomb network has two atomic layer, atoms in different planes, and that can be denoted as black and gray. So this is the one of article which have shown the phosphorene synthesis using black phosphorus, and then they have also demonstrated the synthesis, how it can be scaled up, how we can increase the yield, and apart from this they have also investigated the optical properties. So figure A shows the black phosphorus photograph which were grown basically using chemical vapor transport. So this is a kind of precursor for phosphorene, and this is the crystal structure the figure says. You can see the A direction and the B direction. Basically these two directions are there. So this shows the zigzag direction in A and then armchair in B, sorry, in C, and B is just a direction to indicate the other normal direction. C is the photograph of dispersed phosphorene seeds in a liquid, and figure D is a single phosphorene seed which is having multi-layer or a few layers, and it shows the thickness or the size almost around 2 to 3 micrometer. So how they have synthesized? In synthesis, they have taken a red phosphorus and then they added tin and tin iodide, and then these were loaded in a partially sealed quartz tube under a glove box. Then this quartz tube was sealed under a very high vacuum that was around 4 × 10⁻³ millibar, and with an oxyhydrogen torch. And then it was heat treated in a furnace at 60°. Then after it was taken out and it was opened in a glove box, and then subsequently it was cleaned by using anhydrous acetone, N-methyl-2, pyrrolidone and isopropanol many times. And then it was basically used for different investigations. So here one of the characterization data is there, that is transmission electron microscopy image. Figure A shows, if you see, this is look like a kind of monolayer, and here few layer phosphorene, and they have also taken the line profile which shows the height of or the thickness of the phosphorene seed. Similarly, figure B has few layer multi-layer phosphorene. Figure C shows the mix of this. See, this is the one layer, then this maybe few layer, then this very thick layer, and based on these they have performed the line scan, and based on the count versus observed value was given here. Figure D correspond to the high resolution TM image, and which confirm like the structure is crystalline in nature and atoms are following the hexagonal pattern, and that is confirmed by doing selected area electron diffraction. You can see here the hexagonal pattern is there, and also confirm the crystalline nature of the material. In this study, they have demonstrated the large scale synthesis, and even experiment they have given, like they use a 6 gram of black phosphorus which was dispersed in 800 ml of NMP, and then they use the combination of shear mixing as well as sonication for exfoliation. So by doing this two combination of process, shear and sonication, they achieve the phosphorene sheet, and the sheet is having basically different size as well as the thickness. So they have also counted this, the number of layers versus the count. So the synthesized phosphorene has 1 layer to 4-5 layer combination with the average of 2-3 layers together. Similarly, the size varies from 50 nanometer to 350 nanometer. The average size goes 100 to 150 nanometer. The figure second here, it also demonstrates like if we are going to tune the number of layer, we can easily control the band gap. So what are the difference here as compared to the graphene? If we talk about the properties, one is the structure. The structure is not very flat. Second is the band gap can be easily tuned because this is a kind of up and down structures. The atoms are not very flat. Also, since atoms are not in the plane, so it has very strong in-plane anisotropy, and the carrier mobility is also very, very high as compared to the other 2D materials. This is another demonstration where the thickness of phosphorene was measured, and it is around 0.85 nanometer. Shows here. They have also calculated and simulated the energy gap with respect to the number of layers, and then other properties was investigated in case of phosphorene. For further study, I would suggest to go to the given references. The major problem with the phosphorene is, if you are trying to use this in any device applications, is the stability under ambience conditions. So phosphorene is not very stable, it's highly reactive because it has uncoupled pair of electron, because you are having the sp3 hybridization, and this one electron on the top and bottom is unsaturated, uncoupled, and this is very high tendency to interact with any other species molecules, ions. So therefore, it is not stable under ambience condition. So it can react with oxygen, water, light, or any other molecule also. And after reaction is usually produce oxidized phosphorus or phosphoric acid. So to tackle this problem, the kind of protective coating or the capping layer has been proposed, and which demonstrates slightly better stability. And here basically a kind of atomic layer deposition of a material which is non-prone to basically easily, it should not go for oxidation or reaction. It is capping agent, and such as ALD coated dielectric layer of alumina. This can be also achieved by doing oxygen plasma dry etching to protect the phosphorene. So let's say you have a multi-layer, so maybe 1 or 2 layer or only few layer of the surface side can be exposed with the oxygen plasma, so it is get oxidized, and by this way we can protect the others layer. Or we can coat with graphene or other 2D materials which are stable, and maybe we can dip in some kind of solvent such as NMP, which is not initiating any kind of reaction. So we can make a solution stable by basically putting the solvent together. So that was about the phosphorene. The next material is here, that is stanene. So basically stanene is again the two-dimensional layer structure of tin. So how we can define is if we arrange the tin atom in a single hexagonal layer, similar to graphene, then we can call this is the stanene. So these are the two studies reported at very beginning. The first was epitaxial growth using molecular beam epitaxy over a bismuth telluride substrate. The report was done in 2015. Similarly, the next report was in scientific report. It was also published in just 2016, and they have claimed the synthesis of stanene using the laser beam, and they have also investigated the optical properties. So here you can see the crystal structure of stanene. So where these black atoms are basically the carbon atoms. So on the carbon atom, the growth of stanene was demonstrated. Where you can see the sequential red, yellow, red, yellow atoms are there. So basically, this is not the flat structure again like a graphene. It is having up and down atoms, but they are arranged in the fashion of hexagon or honeycomb. And you can see the side view here. So this is the graphene, and then the tin bottom atom and yellow is the tin top atom. And difference between these two can be denoted as delta, and difference between the tin layer or the stanene layer with the graphene can be denoted as D, and which says delta is the buckling height of stanene and capital D is the interlayer distance between the substrate graphene and bottom tin layer. So this is the first article, epitaxial growth of two-dimensional stanene. Here they have grown the stanene over Bi2Te3-111 substrate by using molecular beam epitaxy, and they have achieved bilayer deposition of stanene film alpha SN111, in which two triangular sublattices stick together and form a kind of buckled honeycomb lattice. And the height between these SN atoms is almost close to 0.1 nanometer, and about 90% of substrate. So they have observed, like when they are doing this kind of epitaxial deposition, only 90% surface is covered with the stanene sheet, and the 10 to 50% space they are observing the islands of tin atoms. Here they have gone through the structural characterization. So one is RHEED pattern of stanate film and intensity as a function of growth time. So A just shows the crystal structure. Here this is the RHEED pattern, and this is the time versus intensity, and this result confirm that the growth is happened within this period when we are having almost 300 seconds. And figure E and G shows the STM topography of SN film. You can see few layers are visible here, and this is the bottom side, and by just putting a line scan we can get the idea about the thickness of the layer. Similarly here they have zoom it, and you can see the clear cut flag formation or the sheet formation, and sheet can be further magnified, and we can see the basically the internal structure of the surface of the stanene. The another study was published in scientific report, the stanene atomic thick freestanding layer of 2D hexagonal tin, and the synthesis was done of few layer stanene using ultra fast laser material interaction. So laser light was interacted with the tin material, and then material was deposited over the graphene, and they have demonstrated, let's say if you remove the carbon top surface and you just put the tin, so what will you are going to achieve? That is basically kind of stanene material. And HRTM image confirm the form of hexagonal lattice and the atomic arrangement. Selected electron diffraction confirm the crystal structure. Similarly, atomic force microscopy image here shows the thickness of the sheet, and which confirm there is a 3 to 4 layers are there. Then optical investigation shows absorption at 196 nanometer, you can see here, and then another absorption as 250 and 225 nanometer correspond to the other two shoulders. And when they have reduced this tin by hydrogen, then this peak is disappears. So that shows basically this peak is correspond to the oxidation of tin. And when they have oxidized it, again this peak came into the existence. So that means this peak is basically relevant with the N2 pi kind of transition, and which is due to the presence of oxygen atom. Similarly, the Raman spectroscopy shows a very strong peak at 149, correspond to the stanene. Similarly, and that is basically related to the in-plane vibration of the tin atom. Meanwhile, they have also observed a broad peak, 85 to 110 nanometer in area, and that is correspond to the out-of-plane vibration of the tin atoms. So that is there for these two material, stanene and phosphorene. So today I would stop here. Thank you very much.